Good morning. I hope you're all safe and healthy. There's no problem. Today we are going to continue with our third online recitation, and we are going to deal with some questions about rings, homomorphisms, and I think lastly maximal ideal. Okay. Uh, have you watched the lecture videos of your instructor? Do you have any questions related to those? Huh? Any questions? Can you hear me? I think there's no problem with the voice. Okay, now let me start with my questions. Please, as always, you can interrupt me and ask your questions. Please use audio to ask your questions, because while I'm writing, sometimes I miss the chat. So let us start. First, if R is a ring with identity, R is a ring with identity, and phi is a homomorphism of R to an integral domain R prime, such that kernel of phi is different from our ring R. Okay. Now we are going to prove that. The image of identity of R, that is phi of 1, is the identity of course, I'm talking about multiplicative identity, identity of the image ring R prime. Okay, we're going to show this one. Do you have any suggestions? Okay, if you don't have any suggestions, then I'm going to start with assuming that phi of 1 is equal to 0. What happens, to see what happens in this case? Assume that phi of 1 is equal to 0. 0 means that the additive identity of the corresponding ring ideal domain R prime. Then what we know is that for all A in R, we can write A as A times 1, right? So this means that if you compute the image of A, then you can write this as phi of A times 1, which is phi of A times phi of 1, because phi is the homomorphism of ring. But here, since we assume that phi of 1 is equal to 0, this gives us that if the image of the identity is 0, then the image of all elements are 0. And in this case, this means that all elements in R lies in the kernel. This means that kernel phi is equal to R. But our assumption tells us that kernel phi is different from R. By assumption, this is not the case. Right? So this means that the image of the identity is different from 0. Okay? So now let Y. So let me write it. Phi of 1 is different from 0. Okay? Now let us take an arbitrary element from R prime. Let Y prime be in R. Okay? Then we are going to show that phi of 1 is the identity of R prime. Then what we have is that phi of 1 times Y. Phi of 1 is an element of R prime. And we can write phi of 1 as phi of 1 times Y. Okay, so phi of 1y is equal to phi of 1 times phi of 1 times y, because phi is a homomorphism. Let us note it down here. Phi is a homomorphism. Okay, then what we have is that just take all the terms to one side of the equality. Phi of 1 squared y minus phi of 1y is equal to 0. We have this equality, and if we take this equality into phi of 1 parentheses, then what we have is that phi of 1 parentheses, phi of 1y minus y is equal to 0. Now remember that, now we have a product here, and remember that this product is inside R prime, which is an integral domain, right? So we have the product of two elements, and the product of these two elements is equal to 0. And since R prime is an integral domain, R prime has no zero divisors, and we know that this one is different from 0. So this one has to be equal to 0, as R prime is an integral domain, and so has no zero divisors. Okay, now what we obtain is that here, okay, what we obtain is that phi of 1y minus y is equal to 0. Okay, so phi of 1 times y is equal to y. Since R prime is commutative as being an integral domain, you do not need to do the other side, that y times phi of 1 is equal to y comes immediately as R prime is commutative. Okay? Do we have anything here? Yes. Okay, let me do this way. Okay, now what we have shown is that we have found that phi of 1 actually multiplying with an arbitrary element of R prime gives us the same element, okay? So this one is implying that phi of 1 is the identity of R prime, okay? So under a homomorphism, the image of the multiplicative identity into in an integral domain is actually the identity. Okay? Do you have any questions? Any problem? Okay. Now is an exercise for you. Exercise. Let R be a ring with 1 and phi from R to R be a homomorphism, be an epimorphism actually, onto be an epimorphism. Then you can show that phi of 1 is again the identity. Identity of R prime. Okay? You can try this one. Okay, any questions? No? Okay, let me here. Maybe this is better. No. Okay. Now, let me continue with my second question. here. What if I change it in this way? Is it better? No. No. Yeah, this is better. Okay. Now the second question. Let R be a ring with 1. Let R be a ring with 1 such that the only right ideals of R are the trivial ones, are the ideal generated by 0 that is containing only 0, the additive identity, and R itself. Okay? Then we are going to prove that R is a division ring. Division ring means that every non-zero element has a multiplicative inverse. Okay? If you add, for example, commutativity over a division ring, then you obtain a field. Okay? You've seen these in your video lectures from your instructor. Okay? Now let us take a non-zero element. Let A be a non-zero element in R. Okay? Then we have seen that we have some kind of ideals that is generated by just one element. Okay, we have called them as principal ideals. Then the ideal generated by A, or you can also show it by denoted by AR. This is the right ideal, right? Is the right ideal? No. Right ideal of R. But we know that A is different from 0. The ideal generated by A is different from the ideal generated by 0. And so, this ideal has to be equal to the whole ring, right? Because we have only two right ideals, the 0 ideal and the whole ring, okay? Then what we know is that R is containing identity. This means that since it is also generated by A, as R is a ring with 1, and R is the ideal generated by A, there exists B in R such that A times B is equal to 1. And this equality gives us that B is the right inverse for A. And so, B is the right inverse for A. Now we need to check that if B is also a left inverse. Okay, then if we can show that, then we say that actually A is an invertible element. And since A was arbitrary, then we have found the multiplicative inverses for every element in R. Okay, now consider the product. Consider BA. Okay, and we can actually write this one as since A times B is equal to identity, we can write this one as B times AB times, this is the identity. This is just the same thing that we do in group theory, some questions, okay, we did it a lot. So, in this case, what we have is that BA is equal to BA squared, okay? Now, for BA, we know that since this is an element from R, for BA we have a right inverse, right? So, there exists C in R such that BA times C is equal to identity, right? Uh, Actually, we're using this one. Okay? The ideal this one. The ideal generated by A is equal to R. Okay? Now what we have is that BAC is equal to BA squared C, because this one was equal to BA was equal to BA squared, so I just multiply each side with C. Okay? Then what we have is that BAC is equal to BA times BAC. Now, this is identity. This is identity. There it is. This is identity, giving us that B times A is equal to identity, okay? So with this one, B becomes also the left inverse of A, which implies that B is also left inverse of A, and hence B is the inverse of A. Okay? Now, at the beginning, A was an arbitrary element. Here we have taken an arbitrary non-zero element, and at the end we have found the multiplicative inverse of A, and this means that actually every non-zero element in our ring R is invertible. Hence, and so, and so R is a division ring. Okay? Do you have any questions? No? Okay. Now let us continue with our third question. Yes. Third question. Now let that be the ring of integers. And P is a prime. Okay, now we are going to show that first that over, if we take the quotient ring of Z with the ideal generated by this prime number P, this quotient ring is isomorphic to ZP. This is very easy. Okay, first let us perform this solution. Okay, now let us define phi from Z to ZB, taking an integer A to its modular class. Okay? Now check that. It is your business to check that. Phi is a homomorphism. This is very trivial. Homomorphism. Oops. Phi is a homomorphism. Now, actually not an homomorphism. This is an onto homomorphism. Okay? Now, if you look at the kernel of phi, this contains here. This contains all integers in Z such that phi of A is equal to the modular class of 0, right? And this contains all A in Z such that the modular class of A is equal to the modular class of 0, okay? And what does it mean in terms of modulo? Nope, I don't want this. Okay, what does it mean? It means that it contains all A in Z such that actually P divides A minus 0, right? P divides A. So this is nothing but A in Z, such that A is equal to P times N for some N in Z. And this is just the same as the ideal generated by P, right? So the kernel of this surjective homomorphism is the ideal generated by P. So make use of the first isomorphism theorem by first isomorphism theorem. If you divide your domain ring by the kernel, first let me write kernel over kernel phi. This is isomorphic to the image. And since it is onto, since this is onto, then the image is that P. And so that over the ideal generated by P is isomorphic to that P. Okay? Do you have any questions with finding the kernel, or do you have any questions about how to show that phi is the homomorphism? Okay, you don't have any. Then let me continue with the second part. The second part is that we are going to show that, prove that P is a field. We are going to show this one by showing that the ideal generated by P is a maximal ideal, okay? By part A, we have that over the ideal generated by P is isomorphic to P. So for part B, we show that the ideal generated by P is a maximal ideal. Okay? Now you know that if you have a commutative ring and if you take the quotient of your ring with a maximal ideal, then you obtain a field, right? Okay. Now, how to show that the ideal generated by a prime in the ring of integers is a maximal ideal? Okay, now assume that I is an ideal of Z such that I is different from the ideal generated by P, and the ideal P, the generated by P, is contained in I. Okay? To show that the ideal generated by P is maximal, we need to show that this ideal I containing the ideal generated by P is actually the whole ring of integers Z. Okay? We need to show that I is equal to Z. Okay? So the easiest way of showing that an ideal is equal to the whole ring, that to show by finding the identity element inside the ideal, right? If you remember, last week we have shown that if an ideal contains a unit, an invertible element, or the multiplicative identity of the ring, then that ideal has to be the whole ring. Okay, we are going to make use of this fact. Okay, now since P is strictly contained in A, I, the ideal I, here, the ideal I, then there exists an element, there exists A in this difference, right? Now, since P is a prime, And since A is not in this ideal, this means that P does not divide A. P does not divide A. This means that the greatest common divisor of these two is equal to 1. This is greatest common divisor. Okay? And you're in integers. This means that you can write this greatest common divisor as a combination of P and A. So there exists x, y, and z such that P times x plus A times y is equal to 1, right? And if you look at this one, this lies in the ideal generated by P, hence the ideal I. And if you look at this part, A times y, A is an element from I of, so A times y actually lies in I, right? So each term lying in I gives us 1. This means that 1 in I. 1 is in I, and so I is the whole ring, and now we have taken P and I, this is equal to Z, right? So the ideal containing, any ideal containing the ideal generated by P must be equal to the whole ring, meaning that the ideal generated by P is maximal. And hence, Z over the ideal generated by P, which is equal to, which is isomorphic to ZP, ZPX. Okay? Any questions? Any problems? No? Okay, fourth question. Let R be a ring containing Z. Containing Z as a subring. Okay? Prove that. Prove that if integers, integers m, n are contained in a proper ideal of R then they have a common factor greater than 1. Okay? And this means that the greatest common divisor cannot be equal to 1. Okay? Now let's, do you have any suggestions? It's an interesting question, I think. Any questions or any suggestions? No. Okay. Now let I be a proper ideal of R containing those integers m and n. Okay. Now assume that m, n do not have a common factor greater than 1. We are going to obtain a contradiction greater than 1. Okay? Then this means that, okay, This means that then the greatest common divisor of these two has to be equal to 1, right? But again, with the same argument in the previous question, there exists xy in z such that mx plus ny is equal to 1. Now, m is an element from the ideal, so m times x is from I. N is an element from I, so ny is an element from I. This means that 1 is in I, giving us that since I contains the identity, I has to be equal to R, which is a contradiction, as we have assumed that I is a proper ideal. Okay? Any questions? No? Okay. Last question. Here, let me change the screen. Our last question for today, but it's a little bit long. Now this is the 5th question. Let R S be commutative rings with identities and phi from R to S be an epimorphism. Okay? Now, first, as part A, we are going to prove that if N is a maximal ideal of S, then the inverse image of this ideal is also maximal in R. Okay? I'm giving you some time to think about it. Do you know the definition of a maximal ideal? I'm using it, but do you know the definition? Okay, take your time and think a little bit. Okay, if you don't have any suggestions or comments or questions on this question, then let me start with my solution. Now, from the last week, we know that phi inverse of n is an ideal, right? Okay, let me first, okay, n is a maximal ideal. It is given in the question, so we assume that n is maximal in S, and consider the parameter of this ideal. Then this is an ideal of R. Okay, now our aim is to show that phi inverse of n is a maximal ideal in R. Okay, now let's our aim too many X. Our aim is to show that phi inverse of n is maximal in R. Okay, so for this purpose, let us take an ideal of R, which is different from this ideal, and show that the ideal that we take has to be the whole ring. Let I be an ideal of R such that I is different from phi inverse of n, and phi inverse of n is contained in this ideal, I. Okay? Now show I is equal to R. Okay? Now, we are going to make use of the fact that actually phi is an epimorphism. Okay, this is onto. So the images of ideals are ideals. Okay, ideal. As phi is surjective, the image of this ideal I is an ideal of S. Was it S? Yes. It's an ideal of S. Then what we have is that N is contained in this ideal, right? Because phi inverse of N is contained in I means that N is contained in phi of I. But here, as N is maximal, we have two possibilities for this phi of I. It is either equal to N or the whole ring. Phi of I is equal to N, or phi of I is equal to S. Okay. Now, if phi of N is equal to, no, phi of I. Phi of I is equal to N, then what we have is that we are going to show that this is not the case. Then for x in I, we have phi of x is in phi of I, which is equal to N, right? Because we have assumed that phi of I is equal to N, and this gives us that, and x is an element inside the pure image of our ideal N, our maximal ideal N. And this implies that actually I is contained in phi inverse of N, but this is not the case because we have taken I as an ideal different from phi inverse of N, and phi inverse of N is properly contained in I. Okay, so since this is not the case, we have left with the possibility that phi of I is equal to S. Okay, now we are going to take an element from R, then phi of X is an S. Okay, only a few lines are left, so let us complete the lecture. Okay, after the connection is gone, I'm going to immediately reconnect, and then we complete our lecture for today. Okay, just we have the second part of this question. Okay, then phi of x is an S, which is equal to phi of I. Which is equal to phi of I. Then this means that since phi of x is inside, I don't know why this is happening today. Since this phi of x lies in phi of I, the image of I, this means that there exists I in I such that phi of x is equal to phi of I, right? And we can make use of the fact that phi is a homomorphism, phi of x minus, no, this is small I. Phi of I, this is equal to 0, right? From the other side, let me write 0 is equal to phi of x minus phi of I. So this is phi of x. Okay, thank you. Now phi of x minus I. Huh? Any questions? No. And since n is an ideal, 0 lies in n, right? This is in n because of this one, as n is an ideal. Okay. Now this gives us that x minus I is inside the inverse image of n. And this is contained in. Okay. Now, actually, we can write. Actually, yeah. Actually, we can write this x as x minus I plus I, right? This is an element from I. We have shown it here. Okay, x minus I is in I. And I was an element from I. This means that an arbitrary element from R actually lying inside I. Okay, so x was arbitrary. Since x is arbitrary, I is equal to R. This means that what we have is that phi inverse of n is properly contained in I. This is R, and we have I is equal to R, means that phi inverse of n is a maximal ideal. Okay? Any questions? And the last one was part B. Let M be a maximal ideal of R, then, no, here. Let M be a maximal ideal of R, then prove that phi of M is either S or phi of M is maximal in S. Okay, we lastly show this statement. Now suppose that, before that, as phi is on 2, we have shown that the inverse of this one, phi of M, is an ideal of S. This is important. Is an ideal of S. Now let us take, J be an ideal of S such that J is different from phi of M and phi of M is properly contained in J. Okay? Now we have this one, phi of M, J, and S. Okay? Now in the first part, we have shown that the preimage of a maximal ideal is maximal in the domain ring, right? No, I'm not doing this one. I'm not taking this ideal. I'm just taking another ideal. Okay, I'm taking another ideal. You have seen in your video lectures that for every ideal in a ring, there is a maximal ideal containing it, okay? Now let J be such an ideal, okay? Let G be a maximal ideal. Ideal containing phi of M. The existence of such a maximal ideal was shown in the video lecture lecture by Mustafa Korkmaz, uploaded, if I'm not mistaken, on April 15. Okay, please check this one. He was using actual Zon's lemma and taking some unions of ideals. Okay, please reread the proof that he had done. Okay, now I took a maximal ideal containing my ideal phi of m. Okay, then what we have is that phi of m is contained in J, and this is, since this is maximal, J is properly contained in S. Okay, by first part, what we have is that phi inverse of J is a maximal ideal of R, right? Because here, what was our statement? Our statement was that if n is a maximal ideal of the image, then the inverse image of this maximal ideal is maximal in R. Okay, so we make use of this fact. By first part, since J is a maximal ideal, the inverse image of J is a maximal ideal of R, but we have this inequality. This means that M is contained in phi inverse of J, but this contradicts the fact that M is maximal, right? Contradiction as M is maximal. Okay? Okay. Do you have any questions? Huh? Any questions? No? Okay, let us together see all the questions. Okay, our first question. If you have any questions, please ask me, or related to video lectures, you can ask. Some question about division ring, some question about maximal ideals and homomorphisms in integers, ring of integers. No? Maximal ideals, homomorphisms, very important. That's one. Any question? Suggestion? Okay. This was a short lecture. I hope you find it you find it helpful and useful for you. Please send me your questions. Okay. Okay. Hope to see you next week. Okay. See you.